there's one more property of estimators that we need to discuss. That property is called the mean squared error. So the definition of the mean squared error is just the expected squared distance between the statistic, so theta hat is our statistic or our estimator, and the true parameter. So think of this as how far do you think you are from the parameter in squared units. Now, there's a very important decomposition that you will run into many times. So it's important for you to have seen this and to understand it. It's called the Bias-Variance Decomposition. And this is one of the things that is underlying all of machine learning is a bias-variance trade-off. So this is, I'm just trying to say, this is important stuff. And so the bias-variance trade-off says this: the mean squared error of an estimator is just the variance of the estimator plus the bias squared of the estimator. So I'd like to go over to the scratchpad and try to develop some intuition around this result. Then I'm going to prove it, and the proof is quite easy. It's just a couple lines long. It's nowhere near as involved as our proof that S squared is unbiased, as an example. And then I'd like to give an illustration of a biased estimator that actually has lower mean squared error than the best unbiased estimator. All right, so let's go over to the document camera. And so what I'm going to just remind you of, so the mean squared error of theta hat is just the expected value of theta hat minus the truth squared. And remember the variance of theta hat. What's the variance of theta hat? Well, this is just the expected value of theta hat minus the mean of theta hat. So let's just write that mu theta hat squared. And remember the bias of theta hat is equal to mu theta hat. So think of this as the expected value of theta hat minus theta. All right, so if we had a single parameter, so theta hat could be a vector also, but let's not go there right now. So let's say we have a single thing that we're estimating. This could be S squared as an example. And then somewhere out here is the value of theta. Okay, so this is the true value of theta. And I'm going to plot the sampling distribution of theta hat. So if we looked across samples, as we did with my sampling distribution lecture last week, we're going to have a distribution around this. And so maybe it's a normal distribution. They are often normal. Okay, so this is the distribution, or maybe let's write this as the sampling distribution of theta hat. So what this is saying is, across my samples, I don't get the same estimate each time. With one sample, maybe my estimate's higher, other times my estimate's lower. But on the average, I'm going to get this value here, which is mu theta hat. So mu sub theta hat, which is the expected value of theta hat. All right, so what the variance is saying is, how far do you think your estimators are from this, the center of the sampling distribution? So this is how far in squared units is the estimator from the mean of the sampling distribution. Now, mean squared error, on the other hand, is how far is the estimator not from this mean, but from the parameter. So how far do you think you are from the parameter? So how far theta hat is from the parameter theta squared. Let me just write that here in squared units. All right, so I could draw a couple estimators for us just to illustrate this. So here's a situation where we have an unbiased estimator. So notice this is equal to the expected value of theta hat, and what I'm plotting here is the distribution of theta hat. So on the average we get this value, which is the parameter. Here the mean squared error of my estimator is just the variance of the estimator, because the bias is 0, so we could say plus 0 squared. So the difference between these two is giving us our bias, and since that's the same value, we're just adding a 0. This picture, on the other hand, is an example of a biased estimator. Now, one of the things that I mentioned is that sometimes we'll prefer a slightly biased estimator if it has lower mean squared error. So I'm going to go get my red pen for a second, and I'm going to draw a different estimator. So here's the sampling distribution of a different estimator. All right, so let's just call this theta hat 2. This is the distribution of theta hat 2. And the way I've tried to draw this is that I have very small variance, and so I expect to be closer to the parameter with this red distribution than I do with the unbiased blue estimator. So I've tried to draw this where the mean squared error of theta hat 2 is less than the mean squared error of theta hat, my original theta hat. And so that's an example of a bias-variance trade-off where I introduce a little bit of bias, but I can reduce my variance substantially to the point where I actually think I'm closer to the parameter with this estimator than with this estimator. All right, so that hopefully gives you some intuition. Sometimes you see pictures like this that I think are kind of good too, where maybe you've got two parameters, theta 1 and theta 2, and books will give you different pictures. And so this would be, if each one of these dots is an estimate, this would be low variance, low bias. In fact, it's probably unbiased the way I drew it, versus a picture that looks like this if we have the exact same units. And we would say this is high variance. So if you think about this as a target, we're all over the place, but on the average we hit the bullseye. So this would be low bias, but high variance. And then a couple more pictures for you. This would be an example which would be low variance, but biased. And then here would be a picture where, we're not even shooting at the middle of the target. So if this is our target down here, this would be high variance and high bias at the same time. So this would be a dreadful estimator. This would be a great estimator, and then we can argue about whether we prefer something that's low variance but biased, or whether we prefer something that's low bias but high variance. All right, so let's go back to the course packet for a second. I promised a proof. So how do we actually establish this result? Well, let's go write this out. So I'll just keep my definitions up here close by in case we need those. So let's take the mean squared error of theta hat. And so what exactly is the mean squared error of theta hat? By definition, this is just the expected value of theta hat minus theta squared. Now, I'm going to introduce a symbol. Mu theta hat is just the expected value of theta hat. So I'm going to do the same trick that we did before, except it's going to look slightly different here. So this is the exact same thing as if I take theta hat minus mu theta hat plus mu theta hat, and then we have to subtract off a theta, and I'm just going to square that whole thing. So this just means the expected value of this squared. Now, let's expand the square on this, and I'm also going to distribute the expectation sign in the same step. So what we end up with here is if we group these two terms together and group these two terms together, we have the expected value of theta hat minus the mean of theta hat squared. Then if we look at the, it's going to be 2 times the product of these. Notice this right term only involves constants. So this is a constant, this is a constant. Therefore, I can just pull that out in front. So this is mu theta hat minus theta times the expected value of theta hat, that's a theta hat there, minus mu theta hat. And then this last term is also just a constant. So it's going to be plus mu theta hat minus theta squared. Maybe I'll zoom in. My handwriting got a little bit small there. All right. Now let's see what we have here. What is this? Well, this is the expected value of some statistic minus its mean. Okay, so some statistic minus its mean squared, well, that's just the variance of theta hat. Now, let's go write out what we have in the second term. It's going to be 2 times mu theta hat minus theta. And then I'm going to write this as the expected value of theta hat minus mu theta hat. And then what do we have here? We have the mean of the statistic minus the parameter squared. This is just the bias of theta hat squared. So let's write that as the bias squared. Now, let's go take a look. What is the expected value of theta hat? Well, this is just mu theta hat minus mu theta hat. So this whole thing right here is 0. Therefore, the second term is 0, and we're just left with the variance of theta hat plus the bias squared of theta hat. I'm going to just give us one more example, and this is kind of it's going to require a little bit of math, and so you know, I don't really expect you to do something like this on the exam, but I am going to show it to you as an example. So I'm going to define. We're going to go back to the exact assumptions that I had in my previous video. So let's say that x1 through xn is a random sample. Now I'm going to add a condition to this. So it's a random sample from a normal population. So nothing I've done so far has assumed normality. Now I'm going to assume normality with the expected value of xi equal to mu, the variance of xi equal to sigma squared. So we could say they're identically distributed. They all have the same mean, all have the same variance, all have the same shape of a distribution. I'm also going to assume that n is greater than 1. So, all right, now I'm going to define SST as the sum of xi minus x bar squared. And consider two estimators. So consider s squared, which is n minus 1 times SST. And I'm going to have another estimator that let's just call sigma hat squared. So sigma hat squared is going to be the more natural thing. So 1 over n SST. So the way I like to think about the variance is, you know, it's the average squared deviation from the mean. So this is literally the average squared deviation from the mean, whereas s squared has this kind of a counterintuitive n minus 1. So it's almost the average, but not quite, because we've subtracted 1. Now, what I want to show is this. The mean squared error of s squared is in fact greater than the mean squared error of sigma hat squared. So this is a really kind of amazing result. So remember, s squared was unbiased, yet it turns out we can have a better estimator if we introduce a bias. Okay, so that's the result that I want to show. So in order to show this, I need a result. So note, if I take n minus 1, it's n minus 1 s squared, and I divide that by sigma squared, okay, this is going to have something called a chi-square distribution with n minus 1 degrees of freedom. And if you go to the Wikipedia page for a chi-square distribution, if you look at the critical properties of this, you're going to see that the variance of this distribution is equal to 2 times n minus 1. So let me just write this out. The variance of n minus 1 times s squared over sigma squared. Now, this is equal to 2 times n minus 1 from Wikipedia. Now what I'm going to do is a little bit of math on this. So I'm going to pull sigma squared out, because that's just a constant. I'm going to pull the n minus 1 out. That's a constant. So n minus 1 squared divided by sigma squared squared is sigma to the 4th. And then what is s squared? Well, s squared is equal to what I just wrote over here, 1 over n minus 1 times SST. So I can bring the 1 over n minus 1 out. 1 over n minus 1, all that gets squared, times the variance of SST. This is all equal to 2 times n minus 1. Now my n minus 1s go away, and so we've just established that the variance of this SST is equal to sigma to the 4th. Let's write it as 2 sigma to the 4th n minus 1. All right, so what I've claimed is that the mean squared error of s squared is greater than the mean squared error of sigma hat squared. So let's go find these mean squared errors. By the way, this is where I need normality. Okay, so this assumes normality. All right, so if you don't have normality, the result's much harder to get at. But remember, I did assume normality, so therefore this result holds. All right, so let's go find the mean squared error of s squared. So the mean squared error of s squared is just going to be the variance of s squared plus 0, because we've already established it's unbiased. All right, so technically 0 squared. All right. So what is the variance of s squared? Well, this is just going to be the variance of SST all over n minus 1. So what's the variance of SST? It's going to be 2 sigma squared times n minus 1. I'm going to pull this out, divide by n minus 1 squared. So one of these crosses out with the exponent, and we're left with 2 sigma squared all over n minus 1. So we now have, oops, this is sigma to the 4th. I copied that wrong. That's 2 sigma to the 4th n minus 1, so this is 2 sigma to the 4th. So we have our mean squared error for that one. Well, now we need the mean squared error of sigma hat. So we first need to find out what the bias is. So the bias of sigma hat squared is going to equal this. It's the expected value of sigma hat squared minus the parameter. So the thing we're estimating here is just sigma squared. So what is the expected value of sigma hat squared? This is going to be, this is SST over n, so 1 over n times the expected value of SST minus sigma squared. So what is the expected value of SST? Well, we have to go back to this result that we had. This is the result that we proved in the previous video. This is SST. And what we showed was this is just n minus 1 sigma squared. So when we find our common denominator, the n's go away and we're just left with minus 1 over n times sigma squared. So what this is really saying here is that we're going to underestimate sigma squared by a factor of 1 over n. So as n goes to infinity, our estimate will be unbiased. It just, you know, larger sample. It takes a larger sample size for this to be unbiased. To approach unbiased. All right. So now we need our mean squared error. What is the mean squared error of sigma hat squared? So this is just going to be the variance of sigma hat squared plus the bias squared of sigma hat squared. So what is this? Well, we already know that this is SST over n. Well, maybe I'll write in all the steps here. So this is going to be SST over n plus, we just found the bias. This is going to be sigma to the fourth times negative 1 over n squared. So that's our bias squared. So I can now write in what is the variance of SST. I can pull n out, so the n is squared. This is going to be 2 sigma to the fourth n minus 1 plus sigma to the fourth over n squared. So luckily we have a common denominator here. So I can write this as, let's pull sigma to the fourth out, sigma to the fourth over n squared. And what I have inside is going to be 2n minus 2 plus 1. So we end up with sigma to the fourth times 2n minus 1 divided by n squared. All right, so we're almost there. We now have an expression for the mean squared error of s squared. We have an expression for the mean squared error of sigma hat squared. And my claim is that this quantity is smaller than. So let's now establish the result. So the mean squared error, this is what I'm trying to show, of s squared is bigger than the mean squared error of sigma hat squared. So what I'm going to do is just write in both of the expressions and get to the point where I have something where it's obvious that what's on the left-hand side is bigger than what's on the right-hand side. So what's the mean squared error of s squared? Well, we showed it over here. So this is 2 sigma to the fourth n minus 1. What's the mean squared error of sigma hat squared? Well, we also found that to be sigma to the fourth times 2n minus 1 all over n squared. So I can multiply both sides by 1 over sigma to the fourth. Those are both positive numbers. I won't change the sense of the inequality. And that's what we're left with. Now, another thing that I can do is multiply both sides by, well, n squared times n minus 1, n squared times n minus 1, and some stuff crosses out. So let's see what we're left with. So here I have 2n squared, and I claim that's bigger than what I have on the right-hand side. So I think we're going to have to expand this square. So this is going to be 2n squared minus 2n, okay, minus n plus 1. So the 2n squareds, if I subtract 2n squareds from both sides of the inequality, they go away. And I have negative 3n over here. So I'm going to bring that over to the other side. So 3n is clearly bigger than 1. So if my n is bigger than 1, actually if my n is bigger than 0, doesn't make any sense to have an n of 1 because you can't compute s squared then. But if I had, so for n greater than 1, 3n is certainly greater than 1, and so I've established the result. That was a fair amount of math. What you want to remember, though, is the big idea. So the big idea is that S squared is unbiased, but sigma hat squared has lower mean squared error. So there's actually a problem in Devore, which I might give as a homework assignment, which is find the the estimator that has the smallest mean squared error. And so it turns out you can actually do better than sigma hat squared with a different denominator. But I think I'm going to save that for the homework.